Okay, osmotic pressure. Osmosis is the flow of solvent from one solution to another through a semi-permeable membrane. The water is small enough to be able to go through the membrane. Dissolved solids cannot go through. And so if we place a semi-permeable membrane in this U-shaped tube and we put pure water on one side and salt water on the other side, osmosis occurs and the water will travel from the pure side to the salty side or to the solution side with a higher concentration. Because the water is traveling only in one direction, that will cause the level of liquid in the solution side, the salty side, to rise, and the level of liquid in the pure water side, or the lower concentration, to go down. Now, if you remember back talking about manometers and gases, what does this difference in liquid levels indicate? A pressure. So the reason that there's a pressure called osmotic pressure, which is pushing the liquid this way. And so even though the force down here from gravity and atmospheric pressure is the same on each side, over here it's the same on each side, we see this rising of the solution here. And the difference in heights between the two columns represents a pressure that's measurable. So here it would be measured. You could measure it in, millimeters of water. It's not mercury, so it'd be measured in water, but that can be converted to millimeters of mercury or torr or atmospheres. So osmotic pressure is this difference. You can also think of it as the amount of pressure you would have to apply to this side to prevent osmosis from occurring. So you would have to put some pressure of gas on this side to keep the liquid from coming up. It will not come up indefinitely because of gravity. The gravity, is fighting against it. So any questions about that? Well, so osmotic pressure is the pressure required to stop osmosis from happening. And that's symbolized with the capital pi. And that equals MRT, where capital M is the molarity of the solution, R is the ideal gas constant. Here we're using our familiar one from our gas law days, 0.08206 liter atmospheres per mole Kelvin, and T is the temperature in Kelvin. So when we take the molarity and the temperature multiplied by this, we end up with atmospheres as our unit. So the higher the concentration of that solution, the higher the osmotic pressure. So calculate the osmotic pressure in atmospheres of a solution containing 1.5 grams of ethylene glycol in 50 milliliters of solution at 25 degrees Celsius. So we see osmotic pressure, and we should think of that relationship. Capital Pi equals the molarity times the ideal gas constant times the temperature in Kelvin. Well, did they give us any of that? Not directly, no, because that would be too easy. That'd be no fun. Do we have what we need to calculate the molarity? Yeah, we do. We have a mass of ethylene glycol, and they gave us the chemical formula because we don't expect you to know that. So we can calculate the molar mass, right? And convert grams to moles. That happens. And then divide by the volume in liters. So let's see. 1.5 grams of ethylene glycol, C2H6O2. And so we need the molar mass of that. So we've got 2 carbons at 12.01 plus 6 hydrogens at 1.008 and 2 oxygens at 16. So this is 62.068 grams per mole. So we've got 1.5 divided by that. We have 0.068 0.024167. I should have 3 sig figs moles. So then, where should I write that up here? The molarity is the moles of solute, which we just calculated, divided by the liters of solution. They gave it to us in milliliters, but we should be good at converting milliliters and liters now. So that's going to be 0.0500 liters. So this molarity is 0.48334 moles over liters. So that's the first term in the osmotic pressure equation, 0.48334 moles per liter. And then we're going to multiply by R, the ideal gas constant, 0.08206 liter atmospheres per mole Kelvin. And when you stick the units in there, then you see, oh, I need that temperature in Kelvin. So that's going to be 298.15 Kelvin. The Kelvins cancel, the moles cancel, the liters cancel. And so the osmotic pressure here is 11.8 atmospheres. What do you think? Is that a high pressure? Yeah. It's a crazy high pressure. Almost 12 atmospheres, 12 times atmospheric pressure. That's a really high pressure. It's high enough that it causes me to go back and look at that and do the calculation again to see if I did something wrong. But no, that's it. So, have you heard of reverse osmosis? It's a method of purifying water. Reverse osmosis is where you apply pressure on one side to force pure water into the other side, and you collect the pure water. So when they say, oh, this is a reverse osmosis system, that's what they're talking about. Is that going to work on something with a molarity like this? Could you do that practically? You would have to apply a pressure of almost 12 atmospheres just to stop osmosis from occurring in the forward direction. Reverse osmosis is only going to work on something like tap water that has a very, very low molarity to start with. So then you don't have to put 12 times atmospheric pressure on it to cause it to flow in the opposite direction.